All right, this is called analytic trigonometry. And give you a little background stuff you need to know before we even start. You need to be good at a few things. Here's factoring. Of course, I know you can factor, but when all of a sudden you get hit with a bunch of trig, and then you're factoring things that have cosecant squared, and you're factoring out a cosecant, it's going to get a little freaky. So we need to make sure you're good at the easy stuff. So what would come out of both of these? 4 and an x. And then what would be left? 6x plus, when you take out the whole thing, you put a 1 back. That way when I multiply it back in like this, that makes 24x squared, and that times that makes 4x, right? Okay, so when you're doing sine squared theta plus a sine squared, you can factor out something. Sine, don't just say sine, you never can have just sine. Sine theta, and then what is left? Sine theta plus 1. Very good. All right, how about on this next one? What can factor out of both of them? Cosine theta. Okay, if I take a cosine theta and I take it out of both of these, I have a 4 minus, and then what would be left? Cosine squared theta. That's right. Because if I take out a cosine from this cosine cubed, all right. Now, if you were doing this problem, a typical book problem, there might have had a 1 here, and then you'd be able to replace this with one of those identities I taught you on Friday. I know that you probably have already lost them, so we're going to be talking about them again today. But there is something that you could replace this with. In case you'd forgotten, it has to do with this. A squared plus b squared equals c squared. So sine squared plus cosine squared equals 1. Remember that from that triangle? I'll show you that again in a minute. But 1 minus cosine would be if I subtracted cosine squared theta from both sides. And then that cancels that, and sine squared theta would equal 1 minus cosine squared theta. So I see a 1 minus cosine squared theta. I can put in that because they're the same thing. So all of a sudden my answer for this one might come down to cosine of theta times replacing this with sine squared theta. All right, so you need to know a lot of stuff to be able to do this. I just wanted to talk about factoring for a minute so that you can picture factoring something out of this. You can factor a cosine out of both parts. All right, that's the new thing I needed you to know there. Next thing, recognizing a difference of squares. Do you remember how this one, at first, most people don't think you can factor because it's only got 2 terms? And all the other ones have 3 terms to factor it into binomial, but this can factor. Do you remember? X and x, and a plus 1 and a minus 1. Remember that? So by that same token, because x times x makes x squared, outside and inside cancel each other out, and the lasts would make negative 1. See, it works? I'd like you to factor sine squared theta minus 16. It's the same exact thing. Got 2 sets of parentheses. Piece of cake. So what did we do on this one? We took the square root of x squared and made x. So we got to just get the square root of this and the square root of that. So it's sine and 4. And now what? A plus and a minus. Raise your hand if you had that one right. Okay, good. So you can factor trig just like you can factor when you had just normal algebra. All right, other background stuff here. If I needed to find a common denominator for these two, I could say 6. So I'd have to take the 3 and times it by 2. And if I do that, I got to times the top by 2. Remember this? And if I want to make this into 6, I got to times by 3 on the top and the bottom. Final answer here would be 4 over 3 times 2 is 6. And this one would be 3 over 6. And now I can add them. Get that? Now I'd have 7/6 for my answer. Same idea. You have to be able to do common denominators for algebra, like variables. All right? So this one's a little intense. I want to start off with something a little simpler, like let's say I had x over 2 plus y over m. If I wanted a common denominator, what would it be? 2m. So how do I get this to be a 2m? I multiply by m. If I multiply by m there and there, it's just like multiplying by 1, so that's okay. Next thing, if I want to take this and multiply it by 2, okay, then my final answer is there's an m2 and a 2m on the bottom. Remember, when you're adding fractions, the denominator just stays the same, so the denominator is 2m. And the top would be xm plus 2y. If you get what I just did there. Didn't even have any trig involved, but it will. That's why I need you to remember how to do common denominators before we get to the trig. Okay, so then look at this one. What's really a problem here is I can't add this and this until I get a common denominator. What would be a good common denominator? Okay, I need your full attention. Some of you guys are drifting. Stay with me. X would be a good common denominator. So how can I get that the bottom to be x if I multiply by x over x? Everybody write that problem down, please, except you can place the 1 with x over x. Because x over x is 1, except it'll be easier. So on the top, it's 1 plus x. On the bottom, it's now x over x plus 1 over x. And can I add those now? The top is 1 plus x. The bottom is the thing I can add. Remember, these are the same, so the denominator is just x. And then I add the tops, that plus that. X plus 1 over x. Now, do you see that I've got a fraction in a fraction? Not really cross multiply. Flip it and multiply. That's true. So I can put this one down here and make it just 1 plus x over 1. Times it by, instead of dividing by, x over x plus 1. Do you see why that is nice? Because those cancel. Final answer is what? X. So the answer is x. And if I go back up here, here's my original problem. And that all simplifies down to just x. Can you imagine how this could have been the same exact thing, except this could have been a cosine squared of x? And this could have been a cosine squared of x? And the same exact thing would have happened. Everything would have canceled just like it just did. And we would, instead of having just an x for an answer, we'd have a cosine squared x. All right, so trig functions are just like any other, not exactly, but they'll follow the same kind of rules for canceling, and you just got to be good at all these little things like making common denominators and such. Question?
Like when you see that, like if it's all, like don't use cosine x.
Yep.
Just get rid of the cosine and just change it out.
Yes, you can, as long as at the end of the problem, if you wanted to take the x out or the cosine x out of there and put in just a plain x for it, as at the end of the problem, same thing. If your answer is like x equals 4, then your answer is really cosine x equals 4. So yes, you can definitely do a swap like that, and that is exactly what we're going to do. So I'm glad you were thinking of that. All right, one last one. I'd like you to just, this should be quick and easy for you, add those two fractions. If you can do common denominators, piece of cake. All right. Now I got ax as the bottom. And on the top, I just add the tops. A plus 2x. Raise your hand if you had that one right. Okay, good. Now, if that same exact thing had been a cosine instead of an x, or a cosecant instead of an a, same exact thing would have happened. All right, moving on. Other background stuff. You got to know how to solve quadratics, because now it's not going to be a simple quadratic like this that you just factor, and hopefully you remember how to do this. X and plus 1 and plus 1, and then my answer is x equals -1. Negative 1 Do you get what I just did there? Remember that? Okay, except it wouldn't say x squared. It would say cosine squared of x. It's the same exact thing. Plus 2 cosine x plus 1. See how this looks way more complicated than the red one? But yet it's the same thing. You got one thing that's squared. You got a normal plane term that's not squared. And then you got a constant. And you got it equaling 0. Then you've got a quadratic. Even if it's got trig in it. All right, so what would you do? What I'd do is change it into the red one. I wouldn't try to deal with that cosine the whole time. I'd just change it to an x and solve the problem, get my answer, and at the end, instead of having x, I scribble this out and put in what? Cosine of x. So could I figure out an answer for cosine of x equals -1? Sure I could. I could use what kind of trig to get that answer? I need a degree. No, analytic is what we just did to get to this part, and then we got to use, starts with an I, inverse trig. You know, you'd go cosine -1 of -1, and you get your answer. All right, grab your calculator and try that one. The question it's asking is, at what angle would cosine be -1? Could you do this from a picture? Sure you could. Here's cosine. At what angle is the cosine -1? Isn't that the same as asking what angle is it right there? So you'd follow it up, and do you remember what's right there? What is it? Yeah, pi, which is also known as 180. Otherwise, if you do cosine with the inverse cosine of -1, did you also get 180? All right. Okay. So, what I'm trying to say there is, if you come across a quadratic that looks like this, let's use sine plus a regular sine plus 5, then you should be going, oh, wait a minute, that looks a little bit like a quadratic. I'm going to change it to x squared plus x plus 5, and then see if I can factor that. And if I can, I'll just do it that way. And at the end, I'll have to remember that whatever my answer came out to be, and this one actually doesn't work, but if it did, and you came out with x equals like 1/2 and x equals 3 or some 2 answers, you got to stick the the sine, what I use, the sine back in at the end. Sine theta equals 1/2, and then use inverse trig to solve it. All right, so there's one thing you got to know how to do. Back to the unit circle, and this is x, and this is y, and this is 1. Okay, nice and simple, right? How about the x changing into cosine, and the y changing into sine? And wait a minute, where's tangent? Well, tangent is sine over cosine. Some other stuff that are basics that you should remember. If I want to change from tangent to cotangent, I would just flip these two. So cotangent would be what over what? Cosine over sine. All right. So that brings up this thing. Because if we go back here, that squared plus that squared has to equal that squared. Cosine squared plus sine squared equals 1 squared. And some people put the sine first. It really doesn't matter. This relationship right here is one of the biggest identities that you have. And what you're creating is a great big list of facts that you can substitute anytime you want. Like you already have some facts in your head. Do you know that that a pound is 16 ounces? So if you were in a problem with pounds, and you had like 4 pounds, do you realize you could stick in a certain number of ounces instead? You can. Yeah. So how about a mile? It's just a fact. A mile is 5,280 feet. So if you're in a problem that has feet, but you got miles, you can stick the feed in for the miles. If you know you have 2 miles, you can go 2 times the 5,280. You just facts, you can replace. So if you're in the middle of a problem, like for instance this,
How many is
5,280. So let's say you had that for the problem. Red writing, that's the problem. And you would go back to your list of all the things you know, and you'd find one that is like, oh, wait a minute. I know one of these.
Is it 1 minus?
If I subtract sine squared theta from both sides, I'll get that cosine is equal to 1 minus sine squared theta. So basically the top here is really just, no, the top isn't 1. What's the top? The top is cosine. And then that's going to cancel that, and the answer is 1. The final answer is 1. Okay. All right. So that's an example of how you can use these in problems. But there's a lot more things that we know based on this. That's one fact, and this is like the biggest one you've got to have straight. You're going to be expected to remember it. You're going to see it again on big tests. You're going to see it in calc all the time. All right, so we need that one. But there's other ones that come from it. Like you can subtract sine from both sides. That's fairly easy. You could subtract cosine from both sides, and you'd have it solved for sine. But what if you didn't want sine or cosine at all? You wanted like tangent. Do you remember what I showed you on Friday? How can you get tangent out of this? Well, you just have to take this fact, the one fact that I need you to remember, and then you can find all these other formulas from it. Okay, like everything is based on this. So everybody write that one down one more time. And underneath it, we're going to divide everything by something. This is analytic trig. This is what you got to be able to handle. If I'm going to divide everything by cosine, then you have to think about what you have left. I know all of you are going to know that that's equal to 1. But some of you are just like, write that whole thing down again, but you shouldn't because it's something different. What is sine over cosine? That's tangent. And the last thing is, what is 1 over cosine? You know that one too. Secant. So now we've got a whole new set. It started out in the black writing with cosine and sine, and now it's in tangent and secant. So what's getting left out that we haven't done yet? Cosecant and something else. Cotangent, and that's what we'll do next. So if I had some fact about cotangent squared, and I don't see it up here, then I can make a cotangent. What is cotangent anyway? If tangent sine over cosine, then so it should be cosine over sine, right? So exactly, divide everything by sine. And then these guys will become 1. These guys will become cotangent. Oops, that equals plus. And then this will be 1 over sine, which is cosecant. So if you had needed a fact about cosecant, there it is. The cosecant is cotangent squared plus 1. Okay, so if you were at a problem that had cosecant in it, that's a prime target. Maybe this is what you should be putting in. Now, you're going to find that there's like a whole bunch of things you could do. Instead of cosecant, couldn't you also, if you had a cosecant in the problem, couldn't you also put in 1 over sine? Yeah, you could. They're the same thing. So which do you choose? Well, it depends on what you want. If you had a sine in your problem, and you could stick this in instead of cosecant, like you have a sine and a cosecant. Like let's say it was like this. Sine squared theta times cosecant squared theta. If you had this problem right here, you should be thinking, okay, I either got to replace sine squared with something or cosine squared with something. Oh, I remember cosine is this, so I can just put in 1 over sine squared right there, and then the sine squareds will cancel each other out. And what would you have? 1. Because if I put in 1 over sine squared theta right here, 1 over sine squared theta, then I have 1 on the top here, would cancel the 1 on the bottom, and the answer would be 1. All right, so that's a typical problem. You've got to know a lot of things and then use them. The reciprocal identities sound scary, but you already know them. Prove it. Reciprocal means 1 over. Fill in the blank. I think you know that one. Sine is 1 over cosine. Remember that? They're evil twins. This is just a big list of evil twins. So cosine. 1 over sine. How about tangent? Use a reciprocal. 1 over cotangent. Get what I'm doing here? If I just wanted secant, secant's 1 over cosine. All right, so reciprocal identities are just to know that everything could be replaced with 1 over its evil twin. All right, the next kind, the quotient identities. These we already talked about too. Quotient just means divide. So this is just these. Sine over cosine is what? Tangent. And then the other one that's like that is just to flip them, and that's what? Cotangent. So those are the quotient identities. Anytime you see a big fraction, it a lot of times comes down to this, where like you'll end up with a fraction where the final answer is sine over cosine, and then you're supposed to know that is tangent. Look for that again sometime later today. All right, so those are the quotient ones. Pythagorean ones, is, again, you got to know this. If you don't remember anything else, you got to remember this. Oh, equals 1. Because you can get all of those squared things out of this. Sine squared, you can get it, its answer is 1 minus cosine. Cosine, 1 minus sine. Tangent, if I need tangent, I got to divide this whole thing by cosine. Because then I'll have sine over cosine right here. But if I divide this by cosine, I got to divide everything by cosine, etc. So this thing is going to give you so many answers right there. All right, moving along. The cofunction identities. This has been bothering me that I haven't talked about it until now, and yet I think it'll make sense to you. Do you get how there's some classic combinations like Batman and Robin? Superman, no, that's opposites. Superman doesn't have like a little helper guy. Yeah, well, they both have man in them, I'll give you that. But did they actually like work together? Oh, okay. All right. So there's like the things that go together well, like chocolate and peanut butter. Really good combination. Another good one is peanut butter and bacon. That is really good. If you haven't tried it, you got to try it.
Oh my God.
And Elvis liked peanut butter and banana. Ever tried peanut butter banana? Somebody did. In honor of Elvis, you're going to have to eat one of those sometime this summer. Okay. Chocolate and banana. Anything with chocolate is going to be good. So I can agree that would be good. Okay, moving on. The cofunctions are like sine and cosine. Don't they sound like they go together? They're not evil twins, but sine and cosine kind of go together. And here's how. And so do tangent and cotangent. Pilot and copilot, right? Okay, so sine and cosine go together in this way. Here's a triangle. Let's say this is 90. Let's say that's a 30. Then you know that's a 60, right? Because they have to add up to 90, these two. What happens if I take sine of 30? Does anybody know what that's exactly equal to? Cosine of 60. See, you could tell that just down deep in your brain. So if I have another situation like that, where except this time, let's say this is 20 degrees, and this must be 70, and I did that cosine of 20 degrees, if I wanted to replace that with something that was exactly equal, I could replace it with sine of 70. You get how those are co-functions? They go together. Yes?
Really quick, how do you make bacon with peanut butter?
So you You make the sandwich, you put the butter on, the butter the bread, then you put the peanut butter on, and then you fry up some bacon, and you put the bacon on top, adds a little bit of crunch. Well, the crunchy's, there's peanut butter making it crunchy too, but oh, telling you, it's really good. If you like bacon and you like peanut butter, you'll love it.
Wait, so you put it on a sandwich?
Yeah, you make like a sandwich.
What, those are the only two things on it?
Yeah,
Oh, I'm gonna make that one.
it's kind of like a bacon, lettuce, tomato. You've heard of that one before, haven't you? A BLT?
There's so much fat in it.
Anyway, now I bet you're going to be able to figure this out. Sine of 30 would equal cosine of 60. All it takes is for this and this to add up to 90. Do you get that? Those are called complementary. Also has the first two letters co. All right. Complementary angles will have this relationship where their cofunction will end up equal. So here's the way to write it without any actual numbers. Sine of theta would equal cosine, but not of theta. You're onto it with your, oh yes, you beat it to it. 90 minus theta. All right. Now, if I wanted to write a book and make it look more complicated, what do you think I'd replace the 90 with? Pi over 2. It's the same exact thing, but that's the way you're going to see it. So what happens if you're running in this problem, you run across this in the middle of some other problem? Like, for instance, it says cosine of pi over 2 minus theta all over sine of theta. And that looks really complicated, but it's really easy because the top could be just crossed off and replaced with what? Sine, because here it is. That is equal to sine of theta. So it's just sine of theta over sine of theta, which equals 1. So these problems look really complicated, but if you know the right thing to substitute in, they'll just cancel off. And the answers a lot of times today are like 1, or negative pi over 2, or just sine of theta. So everything cancels, you just have like a sign left. All right. Odd and even identities. Yes, there's more to learn. Because we had an easy day on Friday, we have to know a lot today. Odd, even identities. All right. So let's first of all try to remember what odd and even ones were. Watch. This would be an even function. Do you remember how if it reflects exactly straight across, that's even? Do you remember how if they reflect this way? Oh, that's going to be a really tough one to reflect. Weird. Let me undo that. Let's do this one, and it would reflect down this way. Do you remember how that kind of a reflection means that the thing is odd? All right. So there's even and odd functions. Do you recognize this green one that I just drew? Is that sine, cosine, or tangent? That's sine. Yeah, that's sine. So what did I just say about that? Is it odd or even? Sine is odd. So here's what you need to write down. Sine of theta equals sine of theta. And leave a little bit of space between the letters and stuff. Can't argue with that. Sine of theta is sine of theta, right? Write that down. Engage. Pencil. Paper. All right, next. What if it's an odd function, like this one is, and there's another odd one that I'll also write in green, is tangent. Do you remember that sine and tangent were together before? They were like a couple before. Back when we had this thing, do you remember the sine and the tangent were both over here? And what was off by itself? Cotangent. Excuse me, cosine. Following me up now. Okay, so there's cosine was off by itself, and the sine and the tangent were kind of together. Well, same deal. Tangent and sine are both odd functions. So here's the special thing that they do. If you have, and you make this sine, this angle right here, negative, then what happens is your answer is just the exact same thing as it would have been normally, except you throw a negative in front of it. What that means is, for instance, if I had had sine of 30 degrees, do you guys all know that one is 1/2? Does that ring a bell? If I change it to sine of negative 30, what do you think happens to the answer? Nope, it doesn't flip. It becomes negative. See, that's this idea right here. See? This negative means that the answer would just be the negative of what it used to be. So if I make this negative 30, the answer is negative 1/2. Okay? What do you think if I just said that the tangent acts the same way, then if tangent of something, let's say tangent of 45, I think I know that one. You guys know tangent of 45? Okay. Tangent is a sine over the cosine, right? And I'm thinking of the unit circle right now, and I'm thinking of that point that goes like this. And this point was root 2 over 2, comma root 2 over 2. And I was thinking that tangent of 45 would be sine over cosine, so it'd be that over that. But as long as they're equal to each other, the answer is 1. Okay, so moral of the story is that's a true fact. So if I stick in a negative right there, what do you think the answer is? Negative. But cosine doesn't do the same thing. If I stick in a negative here, there'd be a negative there. Cosine is different. It has to have its own way. It's an even function. And cosine of some negative degree compared to what it used to be, well, if you just think about it, it makes sense. It can't act the same way as the odd one and have the negative go here. That wouldn't make sense because then it's not different. And it can't just put the negative here, or it'd be like, duh, cosine of negative theta would be, of course it'd be cosine of negative theta. That doesn't do anything. So there's only one other choice. It's the same thing as normal. In other words, if you do cosine, in other words, you should leave it just like this. Cosine of negative theta is equal to cosine of theta. So sticking a negative right here doesn't do anything. Cosine of negative 30 degrees is the exact same thing as what cosine of regular 30 degrees is. And I got a good reason why. Watch. 30 degrees. Cosine of this. Do you get that the cosine of this would be the x part of it? Remember how cosine is x? If I make a negative angle down here instead, make it negative 30, isn't cosine still just the x part of it? You see how it's the exact same thing? They're both the same length. They're both the same distance. It wouldn't change. It's not going to be different at all. So cosine of 30 and cosine of negative 30 would have the same exact answer. And in case you wanted to know, its sine is the y, and that would be the 1/2, and this would be the root 3 over 2. And down here, it would be the exact same thing, except it would be negative 1/2. It's a positive root 3 over 2. So the point is that the cosine, which is the x, is the same in both places. Okay, so I'm giving you a whole big bunch of facts that you need to know. But the point is that if you ever run across a cosine of negative theta in a problem, like right here, you can just say, oh, I'm just going to replace that with cosine of regular theta. Isn't that going to make the problem a little easier? Doesn't have a negative anymore? Because this is the exact same thing. All right, so you're getting a big list of facts. You don't get to use your notes on the test. So some of these things you're either going to have to just brute force memorize them, or you're going to have a lot of the basic ones in your head to be able to derive the other ones. We'll go over them, we'll practice them. But when you're running across a problem and you see like cosecant squared theta over tangent theta, you got to be able to say, oh, well, some of the options are tangent I could replace with 1 over cotangent, right? Or tangent I could replace with sine over cosine. Cosecant squared, that sounds like that one that was sine squared plus cosine squared equals 1, that thing. I could go find one of those to replace it with from the Pythagorean ones. Or what if I saw tangent of theta and somehow it would help me to write in cotangent of pi over 2 minus theta. That's another one of those lists. That's the cofunction thing. So there's a whole bunch of things that are going to be handy for you, like little tools that you can pull out at just the right moment. So like here is a typical homework problem right here, the number 17. And it says, actually wait, I wonder why I started with 17. I'm going to do 17 with you, but we're going to start with the first problem of today's homework, which is number 13, and then number 15. So today, I know we don't have tons of time left, and a lot of you didn't bring your book. You're going to need to bring your book tomorrow. But I'm going to do the first few on the board with you. This is your homework. Your homework starts at number 13 and goes to number 49, and we're doing odds. That's like 20 questions. I know that sounds big, but it's not that bad. And I'm going to do the first several with you right now. So get out a blank sheet of paper and get ready to write. That's a good question. It's off page 451. Page 451. Here. 451. 451. 13 through 49 odds. If it had been 1 through 50, it would have been 25 questions, but there's several cut off at the beginning. It's like 19 questions or something. Here we go. Number 13. 1 plus tangent squared x over cosecant squared x. Now, if you're like me, the answer is just not going to jump out at you immediately. But does that 1 plus tangent squared x remind you at all of that one that goes cosine squared plus sine squared equals 1? Does that kind of ring a bell? All right. So who's got that one somewhere on their paper? Could read me the identity. You remember that one? So read me the identity, though. It's something equals something. All right. There's a fact. He got it out of his notes. Now, when I see 1 plus tangent x, I can replace it with secant. Am I done? No. But somebody here is going to be smart enough to make the next little leap. Oh, there's a thought. Yeah, you could do that, but it wouldn't help you. One, would you say that again, Mr. O? Yes, secant squared is 1 over cosine, and that'll help. Now, you're going to definitely want to use a pencil in these because you're going to try stuff and then it won't work, and then it'll try something else and it will work. So, all right, I'm going to replace the secant with 1 over cosine. Come on. Somebody make the... I know it's the same thing. That's the point. Okay, but we're getting close. So what's the bottom one change into? Oh, if this is 1 over sine squared, because then this will cancel and make that. Now all of a sudden I got 1 over cosine over 1 over sine. So I change it into 1 over cosine times, you flip that one, sine over 1. See what I just did? I just did a fraction and a fraction, and I got this, and I'm almost done. What's the answer? Tangent. The answer is tangent because it's sine over cosine. That is typical analytical trig. It's all theoretical. You're not like looking at pictures. You're not talking about how deep is the hole or whatever. It's all theoretical. And you've got to be able to do substitutions. You got to find the little patterns. You got to recognize, oh, I remember this one. I saw a 1 plus. That must be that Pythagorean thing. Yes? It's a good question. If it's all theory, how does it apply to real stuff? It's all theory because right now you can't use it to solve any really high-level problems because calc is what you need for that. But the calc needs you to be able to do this. See what I'm saying? Calc is very useful. It's like engineers' like mainstay for doing engineering kind of work. Calc's really, really handy. You want to put a man on the moon, you're going to start with calculus. They get into more advanced stuff too, but. All right, so bottom line is we need this for calc. So now let's do number 15 together. This is your homework, so write this one down. Cosine x minus cosine cubed x. Do you remember doing this? I started off the hour with this because I knew that you weren't going to be awesome at it, so I wanted to practice it. That's the factoring. So what comes out? If cosine x comes out, what's left? 1 minus cosine squared x. Have you ever seen that before? This was to the third here, so this one's squared. So 1 minus cosine squared is sine squared, yes. So I'm going to replace cosine x with what? Sine squared x. And now this is another thing that's hard to deal with. Sometimes your answers just don't simplify any farther. You can play around with it. You can like think, okay, well, I can replace sine with 1 over cosecant. It doesn't help. But bottom line is you could beat your head against the wall all day, never get this to reduce any farther. That's it. It's done. Doesn't simplify any farther than that. So that makes the test kind of hard too, because you're taking the test and you think that you should simplify it farther, but maybe you can't. All right. So that's our second problem of our homework. Moving on, we had, there we go, 17. Sine x times cosecant negative x. Ooh, cosecant negative x. Do you remember that stuff with the ones that were odd and even? Those are the ones that had the little negatives. So, can you tell me, cosecant is the evil twin of sine, right? So if sine is odd, this will be odd. If this is an odd function, then I can make it negative cosecant of x. And that negative down, that's kind of on the inside here instead of being in there, then that negative can come to the outside. And can't you replace sine with something? 1 over... Come on, you can do it. What's the evil twin of sine? 1 over what? Cosecant. See how we're going to have a 1 over cosecant here? And a cosecant there? See how they're going to cancel each other out? Just got to don't forget that the negative's still there. See this one? It's just 1 over cosecant. All right, so from there you can handle it. This one, I recognize that kind. Remember these? Those are the co-functions. So instead of cotangent, you're going to replace this thing with its twin, like Batman and Robin, or bacon and peanut butter. What's the co-function for cotangent? Tangent. So you replace this with tangent of x. And now I got a cotangent times a tangent. Ooh, I can do that. You just got to make sure you're careful with the negative. Because, all right, so there's a big list. And if you didn't take good notes today, you'd want to write this page down. It was page 447. Has a big list of all of those facts. The cofunction identities, the odd-even identities. The page right before it, page 446, that's Pythagorean identities. So this big list of identities is also found on the inside cover, front cover of your book. This is the hard stuff. We spend about a week and a half on it, and then we have a test on it. All right, so see if you can keep up.